Now, here is the big thing that I've been hinting at for a while. How do power series work with differentiation and integration? So at this point, we're pretty well invested in the calculus mindset. What are the most important things you could do to a function to understand it? You can take its derivative. That tells you information about its maximums, its minimums, its concavity, whether the function is increasing or decreasing. All of that information is stored in the derivative, so long as the function has a derivative. Not all functions do. Or in calculus 2, we're interested in integration, in accumulation, how much area is beneath that curve of the graph of the function. These are both important things. In fact, they are opposite things, so they are very closely related, differentiation being the opposite of integration and vice versa. Now I have this whole new idea of how I could make a function. I can make a function with a power series. How well does that work with differentiation and integration? Turns out it behaves very nicely. So let's remember what our power series look like. We have some function, call it f of x. The rule that determines this function, right? I'll give you some input f, x, function gives me back a value. The rule for this is to calculate a power series. So I'll have some coefficients, call them c sub n. And I'm centering this power series perhaps at some coordinate a. And I've got to take x minus a to the power n. I'm multiplying by my coefficient. I'm adding up all of those things if I can. As long as I'm in the radius of convergence, this will converge to some value, and that will be the output of my function. Well, this starts to look like a polynomial, just a polynomial that doesn't end because I'm adding up infinitely many things. Can I differentiate or can I integrate by looking at each of those summands separately? And the answer is mostly yes. So this is a very important theorem when working with power series. If we do have a power series and we are working inside of its radius of convergence, remember there'll be some interval where this power series makes sense, and outside of it, that series will be complete nonsense. It will not converge, so it won't be useful for determining a function. As long as we're inside that radius of convergence, then my power series does define a function which is continuous. And it does define a function which is differentiable. And it does define a function I can integrate. How am I going to integrate a power series? The integral of the power series is just the integrals of each of the different powers. So I'll get some constant. Then I'll get some x minus a, where I used to have my old constant term of the power series. I'll have an x minus a squared on 2, x minus a cubed on 3, each of those just using the power rule for integrals. Okay, so that's all very high level stuff. Let's see one example. Here's that Bessel function again from previous lecture. This function is defined for all values of x So this function should be continuous and should be differentiable, and I should be able to calculate that derivative. When I am working with a power series, I just take the derivative of every single summand by itself. So here I just bring down that exponent. And so the derivative of this function has the following power series. Notice that I have to start at n equals 1 because my x to the power 0 just poof, gone when I take my derivative. The summands of my new series are then negative 1 to the power n times 2n times x to the power 2n minus 1, all of that divided by 2 to the power 2n times n factorial squared. Okay, let's look at something more practical.